Okay, so welcome everybody to this session 3B of CAV about concurrency. We're going to have 5 talks. The last one is a tool talk. We are going to hear the pre-recorded videos, and we are welcome to ask questions during the talk, and we can post them on Slack. And then we're going to have about 3 minutes per talk for questions and answers. So our first speaker is Kartik Nagar, and he's going to talk about semantic specification and bounded verification of concurrent libraries in replicated systems.
Hello and welcome to this talk on semantic specification and bounded verification of concurrent libraries in replicated systems. So in replicated systems, data is replicated or copied at multiple locations across the world. Replicated systems provide many advantages, especially for applications which need to cater to a geo-distributed client base. By bringing the data closer to the clients, they ensure uniform low latency across the world. Replicated systems are also available as long as at least one replica is alive, and they also provide built-in fault tolerance. Unfortunately, programming on replicated systems is not very straightforward. The programmer has to worry about a number of factors, such as concurrent accesses to the data at different replicas. When data is transferred or copied from one replica to other replicas, due to the network anomalies, updates to different data items may reach in different orders at different replicas. While consistency models are available, which can constrain this abnormal behavior to some extent, the truth is that a plethora of such consistency models are present, and it is hard for the programmer to pick the right consistency model for their applications. This makes programming on replicated systems very hard. Now, one way to simplify programming for replicated systems would be to have a library of performant and correct implementations of common data structures. So this model of programming has been very prevalent in shared memory multi-core systems, where a number of fine-grained, verified, and highly performant library implementations are already available. For example, implementations in the Java.concurrent package. We can think about migrating these library implementations from shared memory systems to replicated systems. Unfortunately, these library implementations are also going to face the same issues which any normal application would face, and therefore there are many challenges that need to be met. So in particular, we need to consider the impact of the weakly consistent behavior that's possible in a replicated system on this fine-grained library implementations. So to meet that challenge, in this paper we propose an semantics for replicated systems, semantics for library implementations on replicated systems that is parametric in the weak consistency model and precisely captures the impact of this weakly consistent behavior. Furthermore, linearizability is typically used as a standard correctness criteria for library implementations in shared memory systems, but it may be too strong for replicated systems. Therefore, we propose alternative axiomatic specifications for library implementations which are specifically tailored for replicated systems and which precisely capture the observable behavior of these library implementations to outside users. Furthermore, we also propose an automated bounded verification framework which automatically finds violations of these specifications of library implementations. Our verification framework is also parametric in the weak consistency models and therefore takes care of concerns such as arbitrary number of client invocations and multiple consistency models. So in order to precisely illustrate the challenges of moving library implementations from shared memory to replicated systems, let us consider the example of a stack library. So the interface of the stack library consists of 2 methods, push, which takes an argument value, and pop. The pop method returns the last element or the most recent element that was pushed, or it returns empty if the stack is empty, which means that all previous push operations have been matched. We consider Trieber Stack, which is a lock-free fine-grained implementation of the stack library for shared memory systems. So this implementation has been verified to be linearizable for shared memory systems, and internally it maintains the stack as a linked list of values. So to elaborate further, the stack is stored as a linked list of elements, And the Trieber Stack implementation maintains a top pointer, variable called top, which points to the top of the stack, right, or the first element in the linked list. So when a new element is to be pushed, let's say of value v, a new node L is created, to store the value v, and the top variable is updated to point to the newly inserted node L. The next pointer of the newly inserted node L is pointed to the previous top of the stack. Similarly, the pop method is going to update the top pointer to the next node in the linked list, and it's going to return the value v1 that was present in the original top. Now, note that in a shared memory system, this behavior is preserved irrespective of any number of concurrent invocations of push or pop. Now, as a first step towards moving from shared memory to replicated systems, let's consider an event-based representation of the linked list. So in this event-based representation, the value of a variable or the value of a particular location is maintained as a write event to that particular variable. So for example, the variable top contains the node n1 or contains a pointer to the node n1 in the linked list based representation, and therefore it's represented as a write event to the top variable containing the value n1. Similarly, the value field of the node n1 contains the value v1, and therefore it's represented as a write event of v1 to n1.val, and so on. Now, in a typical execution, clients or users are going to invoke different methods of the stack library, possibly at different replicas. So whenever a method of the library is invoked, its implementation is going to run, and the commands of the implementation themselves may be executed on the same or on multiple different replicas. The invocations that are made by the same client are grouped together into sessions. Now consider a basic correctness criteria that the users of a stack library would expect, which we called as addrem. So this stack specification says that the value that is returned by a pop operation must have been inserted into the stack by some push operation, right? So in other words, the pop must be matched to some push in the same execution. This property is definitely preserved in this execution. However, it's violated in this execution because the pop returns the value 0, while 0 is never pushed into the stack in this execution. So we'll demonstrate that the Trieber stack actually violates this addrem specification on a replicated system. So consider this execution consisting of two replicas, R1 and R2, wherein we have made an invocation of push1 on replica R1 and a pop invocation replica R2. Okay. Now we will execute the commands of push and pop in a step-by-step fashion. So first, the push invocation is going to allocate a new node. Let's call the node as L. It's going to write the newly inserted value 1 to L.val. It's going to read the current top of the stack. Let's call it T. It's going to write the value T to L.next. And finally, it's going to update top, right, to the newly inserted node. So it's going to write L to top. Now, when these updates are transferred from R1 to R2, they are reordered by the network so that the write to the top variable reaches the replica R2 first. Now, pop executes on the replica R2 and reads top. Since the write event to top is present, it's going to read L. Now, it tries to read L.val, but the write event to L.val has not yet reached replica R2. Therefore, it's going to read some value, right? Let's say it reads an initial value 0. This is the value that's actually going to be returned by pop to the client, thereby violating the addrem specification because there is no push of 0 in this execution. Eventually, of course, all of the updates will be transferred from replica R1 to replica R2. So this is called an eventually consistent model. So even though the internal states of both replica R1 and replica R2 will be the same, and this guaranteed by eventual consistency, the high-level specification of addrem is not guaranteed. This is violated under eventual consistency. Now, one can think about upgrading the consistency model in order to prohibit this, this anomalous execution. In particular, there's a consistency model called monotonic writes, which ensures that writes are always propagated in session order to all replicas. So note that all the events that are performed within the same invocation are all in the same session. So under monotonic writes, all the three write events performed by the push invocation are in the same session, and therefore they will be propagated in that order to the replica R2. Therefore, the pop operation when reading L.val is actually going to read the correct value, thereby preserving address. However, let's consider another execution under monotonic writes, which involves three replicas. So here, as before, the push one operation is performed in replica R1, but the pop operation changes its replica during its execution from R2 to R3. Furthermore, all the updates from replica R1 have reached replica R2 during monotonic writes, but none of them have reached replica R3. This again also obeys monotonic writes. Now, when pop tries to read L.val from, so first pop reads L, or rather the top variable. It reads L from the top variable from replica R2. But then it changes its replica to replica R3 and tries to read L.val. However, since this particular write event has not reached R3, pop is going to return 0, thereby again violating the address specification. Now, in order to prohibit this particular anomalous execution, we can again think about upgrading the consistency model. So in particular, there's a consistency model called monotonic writes, or rather monotonic reads, which says that writes that are write events that are witnessed by an operation will also be witnessed by later operations in the same session. So under a combination of monotonic reads and monotonic writes, since the pop invocation sees all the writes of replica R1 in replica R2, it will continue to see those writes when the control transfers from R2 to R3, thereby ensuring that pop actually reads the correct value 1 and preserves address specification. However, even monotonic writes and monotonic reads is not enough to preserve the address specification. So in particular, there is a violation involving 4 invocations, which violates ADRAM and which is possible under monotonic writes and monotonic reads. So more details of this violation can be found in the paper. So we find that a combination of 3 consistency policies is actually required to ensure ADRAM. However, interestingly, we also found that there are other specifications of the stack library which can be preserved under weaker consistency models like eventual consistency. So in particular, the specification injective, which says that 2 pop invocations should not pop out the same element, is actually preserved under eventual consistency. So this motivates our approach of designing a semantics and verification framework that is parametric in the consistency policy, and of breaking down the specification into multiple orthogonal axioms or correctness properties. So now we will give a brief overview of our semantics. Right? So our semantics is presented as a transition system omega. It's parameterized by H, L, and psi. So the history H is basically mapping from clients or sessions to a sequence of invocations. The L is the library implementation, and the consistency policy is psi. We break our semantics into language semantics and the replicated store semantics, which must both agree on the underlying low-level read and write events. The output would be a set of abstract executions, where each abstract execution can be thought of as a completed history. Okay? So it basically assigns a return value to every invocation. We can then ask whether or not all the abstract executions which are possible for the given history H and the library implementation L under consistency policy psi obey the specification theta. So as stated earlier, our replicated store is maintained as a collection of events along with binary relations among these events. Different consistency policies can now be specified by placing constraints on these binary relations. Our abstract execution consists of the set of finished invocations and a session order relation. And any specification can be expressed as a constraint on this abstract execution. Our verification framework closely mirrors our operational semantics. So in particular, instead of taking an actual history H, we take a bound k on the size of the history, or the total number of invocations that are present in the history. This basically limits the total number of read and write events that can be generated. We then encode implementation constraints and replicate store constraints, which are going to constrain the structure of these events. So these constraints are encoded in a first order logic formula. The consistency policy psi and specification theta is also encoded in the first order logic formula. And finally, we dispatch the resulting formula to assembly solver. So basically, this answers the question of, does there exist an abstract execution of size k, which violates the specification theta? So we have applied our bounded verification approach on a number of implementations, which are all taken from the world of shared memory systems. For each pair of implementation and specification, in the table we show the weakest consistency policy at which our verification approach did not find any bounded violation within a verification time of 1 hour. So we also show the maximum time that was needed to find the violation for a particular benchmark for any specification and any consistency policy. So in particular, we find that even though we allocate a verification time of 1 hour, if there are actual violations, then we are able to find them fairly quickly. The observation made regarding Trieber Stack continues to hold for other implementations, which is that different correctness specifications generally have different consistency requirements. We also find that important properties like injective and FIFO-LIFO are preserved under comparatively weaker consistency models for many benchmarks. So the main takeaway from our experiments was that since weaker consistency models correspond to better performance, the correctness performance trade-off in library implementations can be very effectively explored by taking into account the actual requirements of the client from the library implementation. So to conclude, in this work, we have investigated the problem of correctness of library implementations in replicated systems. So we have proposed semantics which take into account the effect of weakly consistent behavior of replicated systems weakly consistent behavior of replicated systems in library implementations. We have proposed axiomatic specifications of library implementations which are suited to replicated systems. And we have also proposed the bounded verification approach to automatically find such violations. Our experimental results demonstrate the effectiveness of our bounded verification approach, and we find that the correctness performance trade-off for library implementations can be effectively explored. So thank you for your attention.
So thank you very much, Kritik. I see that we already have a question on Slack. Shaz, would you like to ask it out loud?
Hey, Dana, should I go ahead and answer the question?
Yes, go ahead.
Yeah. So thanks. So Shaz is asking that about comparing our approach with that of replicated state machines, where all requests are basically there is a consensus that's done on all requests, so that there is the same log of operations is maintained at every replica. So the issue here is definitely one of performance, right? So since we migrate this concurrent library implementations from shared memory systems to replicated systems, this concurrent library implementations minimize synchronization. So they basically only perform CAS on limited data items, and there is no consensus that is required on other data items. So what we show is that you can basically get away with minimal consensus by ensuring some weaker consistency requirements, weaker consistency policies on the other data items. And you can still get some useful correctness properties. So I hope that answers the question.
Let Shaz answer. Shaz.
Okay. Can you hear me now?
Yes.
Yes.
Okay. Yeah. Earlier I was not able to unmute myself. Yeah. Thank you for the answer. Makes sense.
Okay, we've got time for one more question. Maximilian, would you like to ask it?
Yes, can you hear me? Yeah, looks like it. So my question is, did you investigate the influence of the bound on the length of the history on the verification time?
That's an interesting question, right? So what we did find was that at smaller bounds, we were able to find a number of violations, but as we increase the bound, probably because of the fact that the state space increases, so we were not able to finish the verification at higher bounds. But we also performed experiments on actual real world systems for a large number of concurrent invocations, and we didn't really find any violations at that time. But how do you actually get smaller verification time for higher bounds is definitely an interesting question.
Okay, thanks a lot. And what follow-up question? What was the length of the bound that you could still manage?
I think we did it up to around 10 invocations.
Okay, thanks.
Yeah.
Okay, should I start the next video?
Yes, please go ahead.
Hello, my name is Bernhard Kragel, and I'm presenting the paper Refinement for Structured Concurrent Programs, which is joint work with Shaz Kadir and Tom Hensinger. In this work, we address the problem of deductively verifying the safety of a concurrent program, which means that no execution of the program should ever lead to an error state. At the core of most proof systems lies the notion of an inductive invariant, which is a property that holds in the initial state of the program, it is preserved across the steps of the program, and it is disjoint from the error states. I'm representing invariants here as unicorns because they are extremely challenging to find for concurrent programs, because they have to capture complex relationships between concurrent computations. Inductive invariants get particularly complex and unmanageable for low-level encodings of a program as a flat transition system. To address the aforementioned challenges, our CIVL verifier advocates layered refinement over structured concurrent programs. Instead of proving a low-level implementation directly, the programmer specifies a sequence of increasingly simpler programs, such that the safety of program PI implies the safety of program PI-1. And so overall, proving the safety of the most abstract program Pn implies the safety of the low-level implementation. The advantage of this approach is that the connection of each layer only requires a rather small invariant that justifies a small program transformation, and thus the program proof is partitioned into small manageable pieces. A core distinguishing design feature of CIVL is that each refinement layer remains a structured concurrent program, which means a program that consists of procedures that have imperative control flow that includes synchronous, parallel, and asynchronous calls to procedures, and where all state updates are encapsulated in calls to gated atomic actions. These gated atomic actions are equally well suited to represent low-level operations as implemented in hardware, like a compare and swap operation, or also more high-level atomic operations, like the logical representation of releasing a lock. Overall, each refinement layer increases the granularity of atomicity by converting fine-grained procedures to more coarse-grained atomic actions. To save on any duplication between the different refinement layers, CIVL represents all layers and their connection together in a single syntactic unit that is called a layered concurrent program. In this paper, we present the foundation for refinement checking over structured programs, which is the basis of a new design and implementation of the CIVL verifier. In particular, we present a new refinement proof rule that is implemented in CIVL. Compared to CIVL's previous refinement proof rule, our new one is more general in the sense that it allows more programs to be refined, as well as eliminating a number of special cases that previously had to be justified independently, but now just fall out as a special case of our single general refinement proof rule. To support refinement checking, we introduce a new specification idiom of named, parameterized, and interference-free invariants that we call yield invariants. These yield invariants establish the context for refinement checking, but are also independently useful of refinement. And finally, we integrate both refinement checking and yield invariants with the linear permission system that allows us to establish an invariant between local variables from different scopes without ever exposing these local variables as ghost global state and actually writing down the invariant explicitly. In the rest of this talk, I'm first going to illustrate the general style of refinement proofs in CIVL, which will make apparent the need for powerful invariants. This leads us to our contributions with yield invariants, and finally I'm going to illustrate the power of local reasoning through linear permissions. Consider the following simple program that shows a spin lock implementation and a client that uses the lock to implement an atomic increment. In particular, the program has a shared Boolean variable b that is used to acquire the lock by repeatedly executing the compare and swap operation to set b from false to true, and resetting the variable from true to false for releasing the lock again. The client, here the procedure incur, first acquires the lock by calling procedure acquire, then calls read and write to access the shared integer variable x, and then releases the lock again by calling procedure release. We're now going to show that procedure incur implements an atomic increment in 2 refinement steps. And by the way, don't worry if you don't follow all the code on the slides, as I'm going to point out the important syntactic features that are supported in CIVL's refinement proofs. So in the first step, we're converting the procedures acquire and release to atomic actions that summarize the acquiring and releasing of a lock. To do so, we hide the low-level implementation variable b and replace it with a more abstract lock variable l that is either equal to none if currently no thread holds the lock, or it is equal to the thread ID of the thread that holds the lock. And so procedure acquire is converted to atomic action acquire that blocks until the lock is available and then sets the variable l atomically to the thread ID of the thread that acquires the lock. And to do so, we actually see that we also introduce a new local parameter into the atomic action that is going to be supplied with the thread ID of the acquiring lock. And on the other hand, action release has an assertion that says that the lock must be held when releasing by the current thread and resetting the lock variable L to none. A unique feature of our new refinement proof rule is that we actually support calls to procedures in a refinement step, which was not possible before. Additionally to the actions acquire and release, we also convert the low-level procedures read and write to atomic actions that explicitly state that a lock must be held when the shared variable x is read or written. And now by instructing CIVL to convert all these 4 procedures, acquire, release, read and write to atomic actions, CIVL automatically rewrites the procedure incur to one where instead of the procedure calls, we now have execution statements to the corresponding atomic actions. And here we also introduce a new local parameter that is representing the thread ID that is now passed to all the atomic actions as appropriate. By annotating the thread ID parameters with linear, we instruct CIVL to first check and then assume that thread IDs are unique. And this allows us to establish so-called mover types that express commutativity properties of those atomic actions. In turn, these commutativity properties allow us to consider the procedure incur to execute atomically, which means that we can pretend as if there are no context switches between the different executions of atomic actions across the procedure. This means that we can now summarize the procedure incur by just applying sequential reasoning and determining that the net effect of acquiring, reading, writing, and releasing equals to just incrementing the shared variable x by 1. And so overall, we hide the lock variable L, and we also eliminate the local variable that we introduced for holding the thread IDs. And so overall, this means that the client of the low-level increment procedure can actually completely forget about the low-level lock implementation and just reason with the high-level atomic increment operation. In summary, a CIVL proof gradually converts low-level procedures to more high-level atomic actions, and the state representation can change in terms of both hiding and introducing global and local variables. To actually perform modular refinement checking, for example, to convert procedure acquire into an atomic action, we have to solve two challenges. The first one being to actually match the different state representations, because the low-level procedure is implemented over the global variable b, whereas the abstract atomic action has an additional local parameter and ranges over the abstract lock variable L. The solution provided by CIVL is to allow the programmer to actually refer to the introduced state in the low-level implementation. So what the programmer writes for procedure acquire is to instrument the code to say, in case the compare and swap operation succeeds, we also want to atomically in the same step update the lock variable L to be set to the thread ID of the acquiring thread in a so-called introduction action. The second challenge is to match the low-level execution steps of procedure acquire to a single high-level step of the atomic action. In particular, the procedure can execute over multiple steps while being interrupted by other threads from the context, represented in black. To abstract from the concrete steps that other threads might take, we need an invariant that tells us something about the intermediate reachable states. In particular, for this example, the desired invariant is that the low-level lock variable b is set to true, representing that the lock is held exactly when L is set to some thread ID, or conversely, when the low-level lock is not held, meaning that b is false, then the L variable is set to none. With this invariant, we can now check that only the final compare and swap operation that sets the b variable from false to true also sets the abstract lock variable from none to some thread ID, and therefore performing the abstract acquire step, while all the other failed compare and swap operations are simulated by skip, meaning an atomic action that does not perform any visible side effects. Our paper provides all the technical details for modular refinement checking. In particular, how to handle the recursive call to acquire. In the rest of my talk, I want to focus on invariants, which are really the powerhouse between refinement. So it becomes as no surprise that we want to have a very flexible and powerful invariant mechanism. To that end, we introduce yield invariants. Yield invariants are named and parameterized. For example, the yield invariant on the slide is called yield x and has a parameter I, stating that the shared variable x should be greater or equal to I. In a program where only increment operations are performed on x, this yield invariant is clearly interference-free. Due to the parameter, the programmer can now invoke the yield invariant at different control locations to suitably control the interference possible from other threads. In particular, in procedure double inc, the yield invariant is called as a precondition at the yield point between the two increments to x and as a postcondition. Now, reasoning with this yield invariant works as follows. At the call to double inc, the caller establishes the precondition by passing the current value of x, let's say x0, as the parameter to I. After accounting for an interference point that has the value of x, the yield invariant guarantees that the new value of x, let's say x1, is greater or equal to the previous value x0. After the increment operation, we now re-establish the yield invariant with the new value x2. And after yet another interference point, we get that a newly evoked value of x, let's say x3, is greater or equal to x2. And now finally, we establish the post condition after another increment that now refers to old x, which means the value of x before the call was initiated. So old x really is a shorthand for x0. And by guaranteeing the interference freedom of the post condition, the caller can now reason after yet another interference point that the value of x, let's say x5, when the call returns, is greater or equal to the value of x at the invocation, just incremented by 2. Establishing the non-interference of yield invariants gets more challenging if global state is connected to local state. For example, in this snippet extracted from a garbage collector, a mutator thread first enters its identifier I into a global set when entering a barrier, and then it removes its identifier again when exiting the barrier. A call to a yield invariant between these two invocations should ensure that the identifier stays within this set, while other threads can execute between the two invocations. Unfortunately, we cannot prove mutator inf to be inductive on its own, because in two instances with parameter I and j, it could happen that I and j refer to the same value. So when I is removed from the barrier set, also j will be removed and does not hold anymore. Instead of baking in the notion of unique thread identifiers, CIVL supports the more general concept of a linear type system. By annotating the parameter to mutator inf as linear, we get the fact that I is different from j in the non-interference check for free. The validity of the linearity annotations is guaranteed separately. For example, if we would omit the linearity annotation on the input parameter to procedure mutator, then we would get a type checking error once we want to call mutator inf with the parameter. In our paper, we show how custom user-defined permissions can be attached to linear values, and how this feature elegantly captures the synchronization protocol between mutator and garbage collector threads. To assess the utility of yield invariants, we ported 30 examples from Wiki-style location invariants to use yield invariants instead. We observed significant proof simplifications, which are largely due to a reuse factor of up to 13. In terms of performance, we can easily construct an artificial example with a linear speedup, and in practice we saw a speedup from 10 seconds to 5 seconds and from 60 seconds to 10 seconds on two of our largest examples. Our tool, the CIVL verifier, is implemented as an extension of Boogie and publicly available on GitHub. CIVL takes a layered concurrent program as input and encodes its refinement proof rule as the safety of a sequential Boogie program. Then the existing infrastructure of Boogie is used to send logical verification conditions to an SMT solver. CIVL comes with over 100 regression tests, and a number of published papers describe non-trivial examples verified using CIVL. The highlighted ones on the slide were written by researchers other than the developers of CIVL. To conclude, we compare CIVL to other verification approaches for concurrent programs. Our work takes its inspiration from TLA Plus and Event B, which popularized refinement reasoning for concurrent programs modeled as transition systems. More recent efforts have developed support for development of verified programs atop the foundation of refinement over transition systems. In contrast, our work develops a foundation and tool support for refinement over structured concurrent programs, rather than flat transition systems. Several other concurrency verifiers do not focus on refinement or layered proofs and target specific programming models or programming languages. Because of the foundation of gated atomic actions, CIVL has the capability of targeting a variety of programming models and was used to verify both shared memory and message passing programs. And finally, while our work focuses on proof decomposition and user interaction, the work on software model checking solves the orthogonal problem of automatically discovering inductive invariants. We hope that these techniques can be eventually integrated in tools like CIVL to increase the automation and decrease the annotation burden for the user. Thank you very much for your attention. I'm looking forward to taking your questions.
Thank you, Bernard. Do we have any questions? So you are supposed to be able to unmute yourself now, so you can also use this media other than Slack.
So I have a question.
Go ahead.
Yeah, hi. So you were comparing with your CIVL-based work with TLA Plus and Event B. So one of the differences I noticed is that TLA Plus is more of a specification language, whereas you talk about programs. Can you say something about that choice? And obviously, working at the level of programs, you're closer to the eventual implementation layer, but correspondingly, you've lost benefit of working at the specification level?
Right. So I think it's a specific kind of design choice to stay at the to use the representation as programs exactly for the reason to really connect low-level implementations to more abstract versions of a program. And I think the representation using these gated atomic actions I was mentioning is actually very well suited to also represent very high-level specifications. So, you know, for example, we have a proof of the Paxos consensus protocol that basically says on a very abstract level just that the state is updated arbitrarily, but in a way that that consistency is kept. So basically, a client of this protocol can forget about all the asynchrony underlying the protocol, but just use this guarantee that consistency is kept at all times.
Okay, so what you're saying is that the nature of your language allows you also to represent and capture high-level specification concepts.
Yes, exactly. I mean, so a gated atomic action basically is this notion of combining a gate, which is kind of a one-state predicate capturing a precondition or some enabling condition for an operation, with a two-state predicate that describes a transition. And in our implementation, we use kind of program code to represent this object, but in the background they're actually translated into a logical transition relation. So it's definitely capable of representing very high-level abstractions and specifications.
Okay.
Okay, thank you. So we don't have much time for other questions. So if you have other questions, please use Slack and the speaker will answer you offline. So
yeah,
we are next talk, which is going to be presented by Noor. Please go ahead.
Hello everyone. Thank you for tuning in to my talk. My name is Noor, and I will be presenting our work on parameterized verification for systems with global synchronization and guards. This is a joint work with Swen Jacobs from CISPA and Christopher Wagner, Milind Kulkarni, and Rupsha Samanta from Purdue. So as we all know, distributed systems are in every aspect of our lives. They are in mobile computing, scientific computing, data centers, banking, and so on. But these systems do not usually work as expected. And this is hardly surprising, since building correct distributed systems is really hard. So let's lay out some of the challenges as well as the typical solutions that have been used in the literature to address building correct distributed systems. So the first challenge is that such distributed systems use complex building blocks. So the verification of the system entails verifying these building blocks. Fortunately, it turned out that in many cases one can carve out the behavior of these building blocks, verify them separately, and then replace them with simpler abstractions when verifying the overall functionality. Second, these systems are parameterized in the number of processes, which calls for parameterized verification, where we verify the system for any number of processes. Unfortunately, this problem is a well-known undecidable problem. And lastly, because of the intricate interleaving between the communicating processes, the proof burden is really high, which naturally called for increasing the automation in the verification process of distributed systems. So implementing these solutions have been in two directions. The first one targets solving the parameterized verification problem using interactive and inductive approaches, often accompanied with abstractions and compositional reasoning. However, fully automating such approaches is not possible, since they inherently depend on having the user in the loop. Another direction to target this problem is trying to solve the parameterized verification problem in a fully automated way. In other words, decidable parameterized verification. Since our work targets this direction, let's go ahead and look at some of the existing work in this area. So naturally, in order to obtain decidability, one have to restrict the system in a specific way. For instance, the type of properties that you would want to check, or the allowed communication primitives, or the type of synchronization that you allow. For example, broadcast protocols target verification for safety properties. They allow broadcasts as a form of communications, but they allow no guards for synchronizations, We will give examples of guards later in this presentation. Second, there are guarded protocols that also target safety properties. They allow for global guards. However, they do not allow processes to communicate, so processes just move internally. And lastly, there is guarded broadcasts that allow for safety properties and does, in a very constrained way, merge using broadcasts and guards by having one specialized guard and two specialized broadcasts. In this work, we introduce the global synchronization protocols, where we also target parameterized verification of safety properties, and we allow for generalized transitions, meaning that we can capture most of the existing communication primitives in the literature, including pairwise rendezvous and broadcasts. And also, we support global guards for synchronization, both conjunctive and disjunctive guards. So this alone makes our model one of the most expressive models in the literature with a decidability result, but we don't stop here. So having all these primitives in the same model allows you to actually enable abstractions. For instance, for some protocol, you can use your global guards to capture the assumes of a protocol and then use your generalized transitions to ensure the guarantees of that protocol, hence enabling abstracting that protocol away. And finally, we allow for practical verification using cutoff results. So a cutoff result is really nice because it can reduce the parameterized verification problem into a verification problem over a finite fixed number of processes. So to summarize, our contributions to address the mentioned challenges is as follows. 1, we allow for an expressive model to enable abstractions. We show that the parameterized verification problem is decidable for a large class of systems in the GSP model. And also, we show that we can enable practical verification using cutoff results. This will be the outline of my talk, so let me go ahead and introduce you to the GSP model. And let us start by looking at the process definition, where we have a finite set of local states, say S0 to S3, and then we have a finite set of communication actions, each of which has the cardinality k, denoting the number of senders involved in this action. And furthermore, each action can be equipped with a global guard that captures a subset of the local state space, and we will discuss the semantics of a guard in a little bit. For example, we have this action A that is a two-sender action and has the associated guard that is the set S0 and S3. And finally, each communication action is associated with a set of local transitions, both send transitions taken by the sender and represented with the double exclamation mark as shown in the figure, and receive transitions that are taken by the receivers and are represented by the double question mark as shown in the figure. A system in the GSP model is essentially a composition of n-identical processes captured by a global transition system M of n that has a set of global states that follow a counter representation, so that each global state marks how many processes are in every local state. For instance, the state Q says that there are 2 processes in state S0 and 3 processes in state S3. Furthermore, we have a set of global transitions that 1. Synchronize all the processes in the system, and 2. Fire with a sufficient number of senders, and 3. Are enabled when all the processes are in the subset of the local state space specified by the guard. So there are 2 types of transitions in this model. I'm going to only expand on the k-sender transitions and invite you to look at the paper for the other type of transitions. So in k-sender transitions, the transition can fire when there is at least k-senders. For example, in this global state Q, we know that the transition based on action A is enabled since all the processes are in the subset of the local state space specified by the guard, and the transition can fire because there exists sufficient senders to take the send transitions, and when the transition fires, we get into a state Q prime where the senders have taken the send transitions and the receiver have taken the receive transitions. Let us examine one system that we can capture in the GSP model. So consider this smoke detector application where upon detecting smoke, a set of processes coordinate to pick up to 2 processes to report the smoke to the fire department. All processes start in the initial state inv, and the internal transition from inv to ask models that a process detected smoke. Note that one or more processes can detect smoke, and at this point the guard G1 is enabled, and one of the processes that actually detected smoke can send a broadcast that moves all processes that detected smoke from ask to pick, and those that did not from env to idle. At that point, the guard G2 is enabled, and the processes in the pick state can use the toSender action choose to pick up to 2 processes to move to the report state, while the rest can move to idle. And finally, from there, the guard G3 is enabled, and all the processes in the system can take the negotiation step reset back to the initial state. While this example may look simple, it does not fit in any of the decidable fragments in the literature. Alright, so now that we've talked about the model, let's try to address if the parameterized verification problem for our model is in fact decidable. So recall that M of n denotes a system with exactly n processes. So when you say for all n M of n, then you're talking about an infinite state parameterized system, and when you try to check if such system satisfies a set of properties, then this is known as the parameterized verification problem, which is a well-known undecidable problem. So in order to show decidability of such infinite state systems, people have used the framework of well-structured transition systems. So a well-structured transition system is essentially a transition system with an infinite set of states and a transition relation over this set of states, as well as a will quasi-order defined over this set of states. And a will quasi-order is an order that is reflexive, transitive, and does not allow for infinitely decreasing chains or anti-chains. More importantly, we call a transition system well-structured if the transition relation and the will quasi-order are compatible. And compatibility is defined as follows. So if you have a transition from some state Q to some state Q prime, then from every state P that is bigger than Q according to the will quasi-order, there should exist a path to a state B prime that is bigger than Q prime according to the will quasi-order. And it has been shown that checking a certain class of safety properties is decidable if the system is well structured. So the question is, can we solve our parameterized verification problem using well-structured transition systems? And the answer is yes. We have to define a reduction from our model to well-structured transition systems. And while there are many factors to this reduction, I'm just going to talk about the most important one, which is finding a compatible will quasi-ordering. First, let's consider a will quasi-order that has been commonly used in the literature for similar models. This will quasi-order says that a state P is bigger than a state Q if it has at least as many processes in every local state. And let's try and use this will quasi-order to prove compatibility for our model. Okay, so assume we have some global state Q where we have 2 processes in the local state S0 and no processes in S1. And say that we have some global transition out of Q, and that this transition is guarded by the guard that says S0. So obviously this transition is enabled since all the processes in Q are in S0, and say that it leads to some state Q prime. Now a state that is bigger than Q according to this will quasi-order is this state P, where we have 3 processes in S0 and 1 process in S1. Obviously, the guard now is disabled because we have a process outside of S0, and this transition is no longer enabled, and we are not guaranteed to get to a state P prime that is bigger than Q prime according to this will quasi-order. To solve this problem, we developed a novel will quasi-order that says that a state P is bigger than a state Q if, again, it has at least as many processes in every local state and the enabledness of the guards is unchanged, meaning that a guard is enabled in P if and only if it was enabled in Q. So under such guard-aware will quasi-order, this state P is no longer comparable to the state Q because in P the guard is disabled and in Q the guard was enabled. So consider a state P that is comparable to Q according to this will quasi-order. So what do we know now? We know that One, the transition can still fire because we have at least as many processes in every local state, and the guard is still enabled. So this transition can fire and will lead to some state B prime. So in order to make sure that B prime is always bigger than Q prime, we came up with well-behavedness conditions that you can check locally on the process definition. So the nice thing about this guard-aware will quasi-order is that in a system with no guards, this will quasi-order works exactly like the old will quasi-order, and the well-behavedness conditions are trivially met. All right, now that we've talked about the decidability of parameterized verification in the GSP model, let's go ahead and talk about how can one do practical verification using cutoffs in our model. Well, one might wonder, since we just shown decidability, what is the decision procedure here? Well, one option is to use the decision procedure given to us by the well-structured transition system framework. However, due to its high complexity, it's not clear that we can have an efficient implementation to this process. On the good side, it turned out that the GSP model actually enables cutoffs. And a cutoff is really nice because you can reduce the parameterized verification problem into a verification problem over a fixed finite number of processes, say C. So if you prove the correctness for this number of processes, then your system is correct for any number of processes. However, while such cutoffs may grow really large, we were able to define a set of sufficient conditions that you can check on the process local definition that will yield small cutoffs and hence enable practical parameterized verification. In the interest of time, I will not go into the details of cutoffs, but I really invite you to look at the paper and check them out. To further show the utility of the GSP model, let me actually give you the big picture here. So we have this project called Discovery that aims to enable automated parameterized verification for systems that build on top of verified components. And the GSP model, with its decidability and cutoff results, serves as the theoretical core for our project. So with this model at hand, we went ahead and developed another model called the Choose model, where we have a set of agreement abstractions. So we abstract protocols like leader elections and consensus, and we support a more user-friendly interface using a DSL and allowing local variables. So the user can then write their systems in the Choose model, and then we can establish a correspondence with the GSP model and obtain the cutoffs and all the benefits of the GSP model into the more user-friendly Choose model and enable efficient parameterized verification in the Choose model. So we actually implemented this and we tested it over a set of benchmarks, including Chubby application, distributed key value store, and so on. And it turned out that all such systems are in fact well behaved, so they fall in the decidable fragment in the GSP model, and that the cutoff values for such systems did not exceed 5 processes, which means that the parameterized verification was reduced to a verification problem that was in fact efficient. So if you look at the verification times, you can see that they are reasonable. To conclude, in this talk, I presented the Global Synchronization Protocols, which is a new model that aims to address some of the common challenges when trying to build correct distributed systems. And we do that by introducing an expressive model that can enable abstractions and showing that the parameterized verification problem is in fact decidable for a large class of systems in the GSP model. And finally, provide cutoff results that enables the verification problem to be practical. Thank you very much for tuning in to my talk, and have a nice day.
Thank you very much, Noor. Do we have some questions?
Right, so Igor is asking if K in the guard, or I'm assuming in the K sender transitions, is constant or it can be parameterized, so 1 over 2. So I think it has to be fixed currently, because in order to be able to represent some of the vectors that characterize how the senders move, we need a finite representation.
Okay, do we have other questions?
Yes, hi, can you hear me? This is Ken McMillan.
Yes.
Okay, so I mean, these are really nice and interesting results, and I'm wondering, you know, let's say that I'm someone who's building a verification tool for distributed programs that, you know, wants to be able to do, you know, refinement proofs down from high-level specs to implementations and so on. How could I go about applying these results? For example, if I had a description of my transition system in first-order logic or something like that, is there a way that I could you know, detect that you know it fits into your model, and you know, tell the user what the cutoff would be, and so forth? Do you see what I'm saying? In other words, how could I take these results and use them in a larger framework?
Noor, are you taking the question, or should I?
You can go ahead if you want.
Okay. Hi, Ken. This is Rupsha. So, so this is, as Noor mentioned, this is part of a larger project, this discovery project of ours. And the goal in this project is to gradually and steadily lower the level of abstraction of systems for which we know how to do automated parameterized verification. While these results are definitely at for a system model that is fairly abstract, again, Noor showed that we have a lower level model, the choose model that he referred to, which is definitely more accessible by users. Okay, so they are closer to programs. The choose model is definitely closer to programs that a user might write. The user can definitely be told what the cutoff for the system is, and whether their whether the system is actually well behaved, right? And we have currently some ongoing work and work under submission in which we have a tool that actually gives the user some feedback as well on how to ensure that their programs written in something like the choose model can be modified to make sure that they are well behaved, or can be modified to make sure that they enable small cutoffs. And really in a longer trajectory, we are looking at using synthesis to help people figure out the tricky aspects that can help them fit their systems into these fragments.
Yeah, that's very interesting. The idea of, you know, being able to give feedback when you have one of these models that has some very specific requirements, you know, of how the user can fit their problem into that model. So I'd be very interested to see that.
Great.
All right, thank you. Let's move to the next talk by Xiao on solver aided. Okay, just let's start.
Hello everyone, I'm Xiao. Today I'm gonna present the paper Solver-Aided Recency-Aware Replication. This is a collaborative project with Farthing Hoshman and Professor Mohsen Lassani. In this project, we present an analysis and synthesis method to produce crack-by-construction replicated objects automatically, given the sequential object and the declaration of its integrity and recency requirements. Our method performs bound inference and coordination condition analysis to guarantee 3 safety properties: convergence, integrity, and recency. Our experiments show that recency-aware objects reduce coordination and response time. Now let's take a look at the replicated object systems. Replicated objects are hosts on multiple servers in distributed system. The state is replicated on all the servers. Clients issue requests to any one of the servers, and the server coordinate with each other to preserve consistency. Replicated object system offers tempting properties such as fault tolerance, availability, scalability, and low response time. That is the reason why they are broadly used in the real-world applications, such as embedded controllers, online services, and game engines. However, these properties came with a price. If not handled with care, replicated object systems can suffer from divergence, steal data, and even more severe integrity violations. Now let's take a look at the movie booking use case we're going to use for the rest of our presentation. The state of the object is two relations, reservation and movie. The reservation relation stores pairs of user ID and the movie they booked. The movie relation stores the movie ID and its available spaces. We have three integrity requirements from the client. The first one requires the movie ID of the movie relation to be unique. The second constraint is the referential integrity, which means that every movie ID in the reservation relation has to be in the movie relation too. The last constraint is the non-negativity of the available space in the movie relation. The two tables below are instances of the object. The arrows represent the referential relation between fields from different tables. We have 5 update methods on this object. The first one is book method. It adds a user and movie tuple provided by the client to the reservation relation. At the same time, it decreases available space field in the movie relation. The cancel method is a dual of the book method. It removes a reservation and increments the available spaces. The increase space method adds a given number n to the available spaces for the given movie ID. And the special reserve method is a dual of increase space. It subtracts n from the available spaces for given movie ID. The off-screen method removes a tuple corresponding to the given movie ID from the movie relation. So what property do we expect from replicated object system? The first safety property we have to consider is convergence, which means that when all the pending updates are processed, the replicas converge to the same state. In this figure, we see the execution trees of two replicas represented by 2 lines. As we can see, if we have book and cancel methods executed in different orders on the 2 replicas, the final state are not equal. In this situation, we do not have convergence. The next important safety property is integrity. It ensures that every method call is executed only on a state where the object invariant are satisfied. In this figure, the book method issued on replica 1 does not coordinate with the off-screen method issued on replica 2. So on replica 2, the book request is executed after the movie has been off the shelf. The state after the book request violates the referential integrity. Even if we have convergence and integrity, object states can get very still and violate users' requirement. In this figure, the method names are represented by their initial letter. If we do not bound the difference between replica 1 and replica 2, the query method on replica 2 will not observe the 3 increase space updates, and the return value of this query will be very still. However, if we do have recency bound, like in the below figure, the third increase space method cannot be executed as soon as it was issued. In this way, the query method issued on replica 2 returns a value with bounded stillness. The recency property not only provides safety guarantees, but also reduces the coordination needed to maintain convergence and integrity. Without recency bound, the special reserve request issued at replica 1 and the book request issued at replica 2 conflict and have to coordinate to maintain integrity. The other 2 requests increase space do not conflict with other methods and can reorder in replica 2. Now with recency bounds in the below figure, we reduce communication by sending the 3 calls in the rectangle buffer in one message. Interestingly, we can even reduce synchronization. Notice that when the special reserve is sent with other calls, it does not need to coordinate with the book call anymore. The buffer can be simply broadcast. By this point, you may wonder, have we already used strong consistency for safety properties? What about the other weaker notions of consistency? Well, indeed, by enforcing the same total order across replicas, strong consistency provides safety properties we mentioned, but sacrifices responsiveness and scalability. On the other hand, the well-known weaker notion of consistency, such as eventual consistency and CRDT, cannot provide integrity and recency properties. Another line of work, CIVL, Indigo, SIZE, and HAMSOS and software are focused on reviving integrity and synchronization avoidance, but they are oblivious to state recency. There are some works like TAG, TARP, FRAC, and PBS considered stillness but did not provide integrity and synchronization avoidance associated with it. To the best of our knowledge, our work is the first one that have all the properties mentioned. This is the workflow graph of our project. In our project, clients only need to provide their desired integrity and recency requirements on the sequential object. Our synthesis to output well-coordinated replicated objects. It includes static analysis to first infer the stillness bound for the elements of object state, and second, infer the coordination relations. It also includes a dynamic analysis that performs part of coordination analysis at runtime. First, let's take a look at the recency-aware relational object language we defined. This language provides a complete set of relational operators, so it is expressive enough for most of the real-world applications. We're going to introduce it through the same movie booking use case. Object is a 3-element record, including a state type sigma, an invariant I on the state, and a set of methods. In this use case, we have 2 relations in our state, reservation and movie relations. The invariant is a predict on the state. It is a conjunction of 3 constraints: unique primary key, referential integrity, and non-negative row integrity. A method is a function from the parameters and the prestate to a 3-element record. The first element, guard, is a Boolean expression that captures the semantic precondition on the method. In the book method, the tuple provided by client must not already be in the reservation relation. The second element is the post state. For book method, the post state of reservation relation is a union of previous reservation relation and the provided tuple. The post state of the movie relation is produced by decrementing the available space field. The capital U here is the update relational operation. For special reservation and increase space method, we use a similar update operation. The last element is the return value. After gather all the object information and requirements from user, we can begin our first step in the static analysis, bound inference and optimization. In bound inference, we take the user-declared recency bound on the return value of methods and infer bound constraints on state elements. The solution to the constraint assigns a bound value to each state element that in the movie booking use case are the 2 relations. We have 3 different query methods. Query space returns available space of a movie. Query reservations returns a set of movies booked by a user, and the query spaces returns a set of movie IDs and their available spaces booked by a user. Now let's take a look at the most complicated query spaces method. It uses a join operation, which is a syntactic sugar for production between the 2 relations and then selection. Here, the recency bound on query spaces method is 6. It means that user wants the return value of the query spaces to be off by at most 6 elements. User also put recency bound requirements on the other methods in the same way. Their recency bound are 3 and 4 respectively. Let's take a look at one of the inference rule we use to produce constraints, the production rule. The judgment of this rule is under delta environment gamma. The stillness of the expression E is bounded by the delta when constraint C is satisfied. The production rule states that the delta for the resulting relation is a multiplication of the deltas of the input relations. In the query spaces method, movie and reservation relation are input relations for the production. Delta MS and delta RS are the stillness for the movie and reservation relations. In this way, we infer that delta MS multiplied by delta RS should be less than or equal to 6, which is the recency bound on the return value of query spaces method. The complete set of inference rules can be found in our paper. After the inference, we have a conjunction of constraints as output. We can have multiple solutions that satisfies all the 3 inferred constraints. For example, a simple solution would be delta RS equals to 1 and delta MS equals to 1. But this solution does not fully utilize the potential of recency specifications. We choose the solution that maximizes the stillness of the state elements, like the solution that we show in the rectangle, so that more calls can be buffered and communication is reduced. The next step is the static analysis on the coordination requirements in order to maintain convergence and integrity. The basic idea here is that conflicting calls need to keep the same total order across all the replicas, and dependent calls have to maintain their causal order with respect to their originating replica. More details about the definition of conflict and dependency relation are available in our paper. We conduct the static analysis to find the conflict and dependency relations between methods with off-the-shelf SMT solvers. With output of static analysis, we generate part of the protocol code. The other part of coordination analysis is proceeded in the runtime using SMT solvers. We declare the conditions for execution and propagation of method calls on the replicated object in the operational semantics, which is proved to preserve convergence, integrity, and recency properties. Here we present the call local rule, which helps us buffer calls locally and avoid communication. Since this call is not immediately coordinated with calls in the other replicas, it has to pass 4 checks for safety properties. The first one is all-state commutativity check, which makes sure that the buffered calls have no state conflict with all the other calls to ensure the convergence property. The calls increase space and special reserve in the rectangle buffer are state commutative with respect to other methods. The next one is invariant sufficient check, which makes sure that the buffer can be executed at any prestate that have invariant integrity. In the execution trace, the buffer calls combined together is equal to a single increase space request, which is proved to be invariant sufficient by SMT solver. After this check, the buffer with the current call can be propagated and executed on the other replicas. The next condition is let permissible write commutativity. We do this check because calls concurrently issued in the other replica do not know the buffered calls. For example, the book request issued on replica 2 is not aware of the buffer on replica 1. So this check ensures that the call issued at other replica are permissible after the execution of the buffered call. These 2 checks combined together ensures invariant integrity. We have one more check inbound to preserve the recency bound across all the replicas. The calls are issued at the current replica but have not been received by other replica, make those replicas still. For example, the calls in the buffer issued at replica 1 makes replica 2 still. In order to bound the stillness of a replica, all the other replicas limited their pending calls. If we distribute the stillness evenly, the sum of weight for pending calls of every replica should be less than epsilon divided by n-1. In the execution trace, we restrict the sum of weights for the request in the buffer. Finally, let's see the actual benefit of recency by experiments on bank account and movie booking use case. The experiment shows that the recency bound, as the recency bound increases, the coordination overhead and response time decreases. We have 2 comparison criteria, coordination load and response time. The coordination load is measured separately for the 3 communication primitives used by the protocol. They are total order broadcast, reliable broadcast, and point-to-point links. We count the number of messages sent through these primitives during execution and compare them with the baseline to calculate the ratio. The baseline is when the recency bound allows only 1 call to be buffered. Now let's take a look at the figure A and C. The x-axis is the recency bound for the state, and the y-axis is the ratio of different types of messages sent compared with the baseline situation. So the lower the ratio, the less communication load, the better. As we can see, the number of all types of messages decrease as recency bound increases. Figure B and D shows the effect of recency on response time. As the recency bound increases, almost all the methods have lower response time. We also compare our recency-aware object with the sequentially consistent object. In these two figures, the lower response time, the better. Over 2 HAMPA provides around 2 times speedup for both use cases. In conclusion, given the high-level specification of a sequential object and integrity and recency requirements, HAMPA synthesizes a replicated object system that ensures convergence, integrity, and recency. We present a relational object language to specify the object and infer optimum stillness bound on the element of state. We also present an operational semantics that defines the coordination conditions of replicated objects and is proved to preserve 3 safety properties. We devise a protocol and implement the synthesis to HAMPA, then evaluate the impact of recency. The experiment shows that recency can reduce coordination costs and provide lower response time. Thank you for listening.
Thank you very much, Shao. Do we have any questions? Okay, so we are a little bit behind schedule, I see. So if there are some questions for Shao, please ask them on Slack and she will answer offline. So let's go ahead and move to our last talk of the session, which is going to be given by Ken McMillan. Brendan, do you have the talk ready? Okay, so in the meantime, let me just say that after this session, we are going to have a breakout session, but it's going to be on another Zoom link. So the Zoom link is available on the CAV pages in the program, and I'm going to put it on Slack also. So don't go away. All right, so let's go ahead.
This talk is about IV, a formal verification tool that's specialized to distributed algorithms, and its joint work with Oded Padon of Stanford University. Now, IV is designed to maximize the use of automation in a proof while at the same time providing certain key properties of that automation. That is to say, predictability, stability, and transparency. When we're decomposing a proof into lemmas that can be handled by automation, it's very important to be able to predict what sorts of lemmas the automation can handle. At the same time, the tool shouldn't fail randomly when we make small incremental changes. And if we can't get a proof, it's important to be able to get actionable feedback that tells me why we're not able to get a proof. We shouldn't just get a result that says unknown. Now, IV provides these properties mainly through support for decidable reasoning. That is, if we put a proof goal into the prover, we should be sure that it's in a language that will allow the tool to always say yes or no, and not to diverge randomly because of the failure of some fragile heuristics, for example, for quantifier instantiation. So there are several aspects of IV that support this: the language design, the use of modular abstraction, the use of tactical proof, and most importantly, actionable feedback. That is, when we have a proof obligation that's not in the decidable fragment, IV can give us specific reasons for that allow us to reorganize the proof. So here's the overall architecture of IV, and we'll look at each component and see how the components work together to produce a proof. So we start with the IV language. Now, this is a procedural programming language that manipulates pure first-order functions and relations. And the reason for this is that we want to have as much expressiveness as possible, while at the same time making sure that the verification conditions always fall within pure first-order logic. Moreover, IV gives us reactive modules with assumed guarantee specifications. And that allows us to hide behind an abstract interface all of the internal implementation state and also the theories of the data types that are used in the implementation. And hiding of theories is very important for allowing decidable reasoning. So the first thing that IV does in the proof is it breaks it down into local proof obligations for each individual module. In other words, it does a modular decomposition. And it hands those proof obligations off to the tactical engine, which has the job of coordinating the use of tactics to discharge proof obligations. And the most important tactic is invariant checking. That is, we take an inductive invariant that's supplied by the user, we produce a verification condition for it in logic, and we give that to Z3 to prove. However, we first give it to the so-called fragment checker, which will examine it, and if it's not within Z3's decidable range, it will give us a reason. It will point to a subformula or a particular function that we need to abstract in some way in order to make the proof goal decidable. Another approach that we can apply is so-called eager abstraction. That is, we can abstract an infinite state system to a finite state propositional logic system, and we can use a model checker like ABC to check it. Now, this has the advantage that we can potentially find large parts of the inductive invariant in an automated way, whereas at the same time, finite state model checking is relatively predictable and stable as compared to infinite state model checking. Now, if all else fails, we can fall back on logical reasoning, on logical tactics. So in this case, we'll be giving a more detailed, manually guided proof. For example, we might manually instantiate a quantifier in order to push the verification condition into the decidable fragment. And of course, we want to do that as little as possible, but we have this kind of manual reasoning as a safety valve in case our overall proof decomposition doesn't work. Now, once we finish the proof, we can then extract parallel executable code that communicates over a network. And this is done by translating into C++. And to do that, we take IV's value-based language and we introduce pointers and references. This is to avoid copying. And when we do this, we use a number of techniques that are used in Rust and C++. For example, borrowing of references, move semantics, copy on write, and so forth. And that allows us to get an efficient implementation that doesn't do too much copying. Whereas at the same time, when we do the proof, we don't have to reason about pointer aliasing, which greatly simplifies the proof. Now, finally, Ivy has the ability to generate modular specification-based testers. That is, given a module, we can produce random inputs that satisfy its assumptions and check that its outputs satisfy its guarantees. And this is a nice way of doing unit testing because, in effect, because of compositionality, it exposes all system-level bugs at the unit level. So here are some applications of Ivy. It's been used, for example, to verify implementations of various distributed algorithms, such as consensus protocols and Byzantine agreement, where we're able to produce a verified implementation that has reasonable performance with also reasonable proof effort. It's also been used for specifying and testing implementations of various protocols, such as the memory hierarchy protocols of the RISC-V processor architecture, and also the quick internet transport protocol that's going to be used for HTTP, where a number of interesting bugs, including security bugs, were found. So to conclude, Ivy's language, module system, and proof tactics are designed, on the one hand, to maximize the use of powerful proof automation tools like Z3, but also to maintain predictability, stability, and transparency that are needed to construct large proofs and to generate sufficiently high-performance code. So for this purpose, Ivy integrates a variety of technologies having this property, right, with the goal of maximizing the productivity of formal development within the particular application domain of distributed protocols.
Thank you very much, Ken. Do we have any questions for Ken? I guess it's hard to come up with questions on such a short talk. Ken, do you want to add something? Okay, go ahead.
Can Ivy generate concurrent C++ code?
Well, so by that you mean shared memory concurrent code. Is that correct?
Or any kind of concurrency.
Well, it generates code that's distributed. In other words, you can take your Ivy program, and from it you can produce a parameterized collection of processes that might run on different servers or on different processes within your operating system and communicate over the network. What it doesn't do is it doesn't generate threaded code where you have different processes that are sharing memory. Ivy is really specialized to distributed protocols.
I see, great. Thank you.
maybe as a follow-up to that, so how do you do this mapping to kind of say what operation on the logical representation will be an operation like, you know, sending a message versus some local state update? Like, is there some configuration that you have to supply how a program will be distributed and executed on a network, say?
Well, right. Okay. So there's, of course, you can have local state updates, but in order to distribute the program on the network, there's a couple of things you have to know. The first is that executing these atomic actions concurrently will give you consistent semantics, and that's something that Ivy checks for you based on the left movers, right movers argument. The next question is, well, how do you actually configure those processes on the network? In other words, you know, you have to say, where am I going to launch the processes? What are their network addresses, and so on. And that's something that that's something that has to be supplied at runtime. So those things are just parameters to those processes that you have to give them at runtime. And Ivy doesn't do anything to verify that you've actually correctly configured those processes on your network. But that would actually be a very useful feature to be able to have, is some kind of configuration system where you could guarantee that you've actually say you launched your processes on you know, a cloud service like AWS to show that you've actually configured them correctly.
Thanks.
All right, so this basically concludes the session. Thank you for the speakers. Thank you all for attending this session. Don't go away, so you can log out of this meeting, but join the breakout session where you can discuss with whoever is randomly joined with you on your session. And we will see you there shortly. Bye-bye.